Astronomers have confirmed the existence of over 6,000 exoplanets. Yet, the absolute best image ever captured of one remains a single blurry dot. We are searching for more than light. We want to map the surface geography of these worlds, identifying vast river systems, towering mountain ranges, or the lights of a civilization. Physics creates a harsh ceiling for traditional telescopes. To capture high-resolution surface details on a planet light-years away, a space telescope would require an optical mirror 90 kilometers wide. This creates a second, more severe constraint, the contrast problem. An Earth-like planet is roughly 10 billion times fainter than the star it orbits. It is the observational equivalent of trying to photograph a firefly next to a stadium floodlight from hundreds of miles away. Traditional optics cannot overcome these scales. To see an alien world, we have to bypass the mirror problem entirely by using the sun itself as a lens. Albert Einstein provided the mathematical foundation for this in 1915. He described gravity as the physical warping of space-time caused by mass. The sun acts as a gravitational lens, funneling a distant planet's light and magnifying its brightness 100 billion times. This focused light converges at a specific region. The focal line begins 550 astronomical units from the sun, over 3 times the distance to Voyager 1. From this vantage point, the planet's image is no longer a dot. It projects as a glowing halo around the sun called an Einstein ring. This alignment removes our 2 biggest obstacles. We are focused purely on the planet's light, which avoids the glare of its host star, and we gain the resolution of a 90-kilometer telescope without building one. Distance is the new limit. At 550 astronomical units, a mission using traditional chemical propulsion would take 110 years just to reach the focal line. To compress this journey into 20 years, mission designers proposed the Sun Diver maneuver. The spacecraft flies towards the sun and unfurls a 32-kilogram sail made of carbon nanotube film, 70 times thinner than a human hair. At its closest approach, the momentum from the sun's own photons pushes against the sail, accelerating the craft to 125 kilometers per second. Using solar radiation for propulsion transforms the mission from a multi-generational dream into a target achievable within a single scientist's career. A 20-year journey creates a high risk of hardware failure. If the primary telescope malfunctions upon arrival, the entire mission is lost. The String of Pearls architecture solves this through redundancy. NASA would launch annual swarms of autonomous CubeSats, forming a relay chain that stretches from the sun out into deep space. Looking back at the Einstein Ring requires pointing a telescope directly at our sun, which introduces the blinding interference of the solar corona. The CubeSats move in a grid. 4 capture the Einstein Ring, while a 5th measures and subtracts the sun's glare. Then an algorithm applies general relativity in reverse. It mathematically unwraps the ring, reassembling the photons into a clear map of the planet's surface. This process turns chaotic, warped light into a usable record of a world we could never reach. For our neighbor Proxima Centauri b, this method would yield a resolution of 1 kilometer per pixel. That is enough to distinguish between continents and oceans, or track the seasonal growth of vegetation. This amplification works in both directions. If the sun can focus incoming light, it can also act as a cosmic signal booster for any laser we fire outward. This creates the potential for a solar system-scale relay. By placing a transmitter at the sun's focus, we could send data across light years at the speed of light with almost no signal degradation. While light speed latency remains a factor, the energy efficiency is unmatched. Transmitting data this way requires only a fraction of a watt compared to the massive power output required for standard long-range radio. If advanced civilizations exist, they may already be using their own stars as relay nodes. We have simply lacked a receiver in the correct focal line to listen to the traffic. Implementing the Solar Gravitational Lens Telescope would do more than prove life exists elsewhere. It would give us the first functional tool to bridge the vast distances between stars and finally observe the neighbors we've only been able to imagine.